Well, thank you so much for having me. Can everyone hear? Great. Thank you to the organizers for setting this up, and looks like the computer situation resolved itself in the end. Okay, so I'm happy to be talking about persuaded search today. Okay. And today's talk is actually going to be based on two papers. So the first is Persuaded Search, the same name as the talk, which is going to account for almost everything that I say. This is joint with Teddy Mekonnen, who's my colleague at Brown, and Zeky Murra-Anton, who recently graduated. He was one of our PhD students. And the remaining 2% of the talk will be a new paper that Teddy and I are working on in very much the same vein. So really, the basis for this talk was reconsidering of McCall's original search model. And so just a reminder, the idea is you're a searching agent. There's a pool of goods. Every day you draw one good from this bag. Upon drawing this good, you see the value of this good, and then you choose to either accept this good, continue your, end your search, or reject the good and continue your search. Okay, so it's an irreversible decision to uptake the good. And okay, let me say something that's, let me highlight one thing that I said here, which is that we observe a good's true quality upon sampling it, which here's a kind of tautological statement, which means there's no uncertainty once you sample the good. Okay. But of course, in reality, it might be that when you sample a good, some uncertainty persists. And one way that you might think of resolving some of this uncertainty is to acquire more information, perhaps from a third party. Okay. So here's the here's a motivating example we can take with us for this talk. Suppose you are a firm, you want to hire for a single vacancy. Ideally, you'd like two things. You'd like to hire a very good employee. Good employees are better than bad employees, right? So high productivity. You'd also like to hire a person sooner rather than later. You don't want to have the position sitting vacant for 1,000,000 years just to find a genius. You'd rather kind of settle for something, perhaps after 1 year and get someone a little bit less genius, but still competent. Okay. And so the timeline is, the firm meets an applicant, observes the productivity, and then chooses to hire and the search or continue on. But of course, in reality, and this is what I was saying before, maybe you don't observe the productivity. Right? So as it turns out, more than 80% of US firms depend on pre-employment tests when they're doing hiring. These tests are provided by third-party information brokers. They design and administer the tests, and the tests can go after a number of things. There might be cognitive assessments, there might be job simulations, there might be personality tests, and for low-skilled jobs, these tests apparently are actually decisive for hiring. They don't really affect wages. It's just, do you get the job or not? You might imagine many other situations where you rely on a third-party intermediary. So if you're trying to buy a used car, you might go to Carfax. I live in Rhode Island. I don't have a beach house. If anyone would like to give me money, I would be happy to buy myself a beach house. But conditional on wanting to buy a beach house, I might worry about flooding. And I might consult, I look at a house, I think, oh, I like the bathroom, but is it going to flood? Let me consult with the geologist, right? So I can, in many search situations, we have third-party information brokers who play some role. Okay. So for today's talk, I'm going to assume that all information, all uncertainty persists at the X-interim stage. So I sample a good. By myself, I learn nothing about this. Okay, sampling it doesn't provide any information. But there is a principal who serves as an information broker who can design and provide me with information. And I can, use this information in my job search. For most of the talk, I'll consider a single information broker. This information broker's goal is to maximize their profit. And later I'll talk about competition a little bit. And so really what we're doing here is we're marrying information design and sequential search. And this will become clear as I go on, but let me kind of briefly talk through the timing in each period. So the agent is going to sample a good from the pool. The principal will design a test and offer it to the searching agent. The agent can either say, yes, I want to buy this test, or no, I don't want to buy this test. Buying the test provides a signal as is distributed by the test that's been designed, and the agent can choose to stop her search or continue. Right. So we're basically the two middle points here are the kind of info design, and the first and the last point are kind of the classic McCall search. And the reason that things are perhaps not obvious is that, well, the principal is profit maximizing. The principal doesn't actually care about the outcome of the search. The principal just wants to maximize their own profit. And so the question is, how much information should we provide? And also, how much should we charge? And these are going to be kind of non-obvious questions that are, or the answers to these are perhaps going to be non-obvious, but I'll let you decide for yourselves. Okay, so as a kind of very easy benchmark, we can see what happens if the principal has commitment. If they can say, look, I'm going to be able to commit to this contract I offer you also in the future. And what we see is that we have an equilibrium here where the principal sells full information in perpetuity for a one-time fee. We can think of this as selling the testing technology to the searching agent. Okay? And it's pretty straightforward to see, look, okay, Harry's an information broker. He charges me a huge upfront fee, but sells me this technology. After that point, it's a sunk cost. I'm going to search as if I had full information for free. And then I'm back in McCall's world where we basically don't have to worry about Harry. Okay, so search would be efficient. Of course, Harry would extract the full surplus from me, but fine. If efficiency is search is efficient, we're in good shape. What happens if there's limited commitment? So Harry can only say, I'm going to offer you this contract today. Tomorrow we'll repeat the process, but I can't promise you a contract tomorrow. I can only promise you the contract today. You might think this holds because, well, in these pre-employment testing, we have to, if we're testing coding skills or something, it might be that the test that I offer today is not really going to be relevant 6 months from now or a year. Okay, so here are some things that Harry has to consider. He wants to sell this test to me. Okay, so he wants to make money. Now, if he charges me a lot of money, and I anticipate that I'm going to be charged a lot of money in the future, then my continuation value for searching is lower, which means I just want to get out of the game quickly, right? The future doesn't look quite so rosy. So that means that I'm going to stop perhaps earlier than Harry would want me to. He wants to keep pumping me for money. On the other hand, and so of course there's a trade-off here where if he offers more information, he can charge me more money. But if he provides me less information, okay, then it might be that the entire surplus from the relationship is lower, right? The information search without much information is not as useful as search with a lot of information. So he can't squeeze me for as much. So it's not obvious that we want to provide more information or less information or the right type of information, how much to charge. Here's our result, and here's the result that I'm going to build to for much of the talk, which is even with limited commitment, we have qualified good news, at least in terms of efficiency. There's an essentially unique stationary equilibrium. This equilibrium has the following features. Number one, search is socially efficient. Okay, so we're not creating any distortions. Number two, the principal still extracts the maximum surplus. Okay, so this is, so far, we're exactly the same as the world with commitment, where it's just a one-time fee. And the third is that actually full information will not be provided. Okay, in fact, there's going to be some clever pooling of low types with low type goods with kind of medium type goods to both keep the agent searching when they're supposed to search, but also stop them from searching when they're supposed to stop. So this is really the end of the introduction. I'll jump in if there are no questions. But you know, basically the finding is, even throughout these trade-offs where things look a little complicated, it's still the case that in the essentially unique equilibrium, the principal is able to squeeze the agent forever. Okay, so I'll jump into the model. I'll talk about some preliminaries, and I'll actually go through maybe in a little bit more detail how we can kind of view signals as posterior means. I think that might fit with the theme of this workshop and maybe useful tools. I'll discuss stationary equilibria, and I'll give you a proof sketch for the result I just showed you. I'll touch on some extensions, and then I'll conclude. And before doing so, I'll show you some names of people who have done some great work. Okay. So an agent with unit demand searches sequentially. There is no recall. Each period, where periods are going to be indexed by generic T, that the agent remains in the search market, a few things will happen. Number one, she will draw a new good at random. Okay. That good is going to have type theta T, which is drawn on from this interval theta, theta lower bar to theta upper bar. We're restricting the theta upper bar as positive so that there's actually some reason to stop. This will be unobserved, okay? It's known that theta T is drawn according to some distribution F, which we're assuming for simplicity to be absolutely continuous, and that this distribution has a prior mean of mu naught, of m naught. Now, the principal can design and sell any signal it wants for free. In each period, the principal will make an offer, a take it or leave it offer, which has three components: a price, which is just a positive number, a signal, and a set of signal realizations. So this ST, oh, that's not going to work, huh? Okay, so yeah, okay, so this ST is just the set of signal realizations. Pi is going to map the truth into distributions over signal realizations. So pi is just a signal. S is the unfortunate type space notation that we have to carry around for a little bit. But I don't think there's anything non-standard here. And here's the timing. Okay, so just putting it all together on one slide. First, a new good is sampled. The principal proposes a contract. The agent can choose to buy the contract or not. Okay? If she buys the contract, which means we take the upper branch, then the agent observes a signal based on the true quality of the item and also the signal that's been sold. Or if she doesn't buy the signal, then she observes nothing new. At either from buying or not, the agent can choose to stop, in which case the game ends. That's dt equals 1, or continue, in which case we repeat the process in the next period. And here are the ex post payoffs at time t. So if AT equals 1, which means the signal is purchased, the principal gets PT. If dt equals 1, which means the agent stops his search, then he gets theta t. And of course, if he pays, then the money transfers over. We'll assume that the agent and principal have a common discount factor delta. Everything would be the same if instead of this discount factor, we had a search cost, an additive search cost that the agent had to pay. So think of this as like, I don't like to read CVs, so that's the cost it takes me to read the CV. Or we could combine these two. So we have both, this exponential time discounting and the cost of reading CVs. That won't really matter. I'm just going to stick with the first one for today's talk. Okay. And the last kind of preliminary before jumping into, I think, some of the more interesting stuff is that, look, it's going to have to be the case that we're going to have to put some restrictions on the discount factor and the type space and the mean. For example, if it's just the case that the discount factor is so high and the gap between the best and the worst quality item are so small, then yeah, even if you draw the worst quality item today, you'd rather take that than wait for another period and get the best quality item, even if you were guaranteed. We have a type condition here. It's not super interesting. We're just going to assume that we're in a situation where contracting is possible. Okay. So now let me talk about signals. So far we have this I and this S, a little bit annoying. Okay. And if the agent rejects this contract, right, what's her expected match payoff if she were to accept the good? It would just be equal to the prior mean, mu naught. If she accepts the contract and she observes a score, what is that going to do? Well, she's going to have some new expectation. Call that MT. But really, if you're deciding to continue search or stop search, all that you care about is the expected value of that item at the time that you're making the decision. All that matters is its posterior mean. And so the direction we're going is we want to translate this pi and this S into something that looks like a posterior. Luckily, Blackwell told us a lot about how to do this. So each signal, pi S, is going to induce some distribution G over posterior means, such that G satisfies what is now known as being a mean-preserving contraction of F. This is majorization constraint. I'll show you in a picture. We're actually going to go one step further. Things look kind of nice here. And we'll let this script G of F be the set of all mean-preserving contractions of F. Roughly speaking, what does this mean? We take some distribution. All we can do is we can offer you full information, or we could kind of, offer you less information. The mean-preserving contractions are just the set of things that are less informative than that. Okay. And so, based on this, and then really, Rothschild and Stiglitz maybe were the first in economics to bring this up. We can think of this. We can use this mapping to basically restrict our attention to signals and to contracts, excuse me, that are of the force PG instead of P pi S. Okay. And as we'll see, I can take a derivative of things that look like G more easily than a pi in S. Okay. And so here's the one more step before we can show a nice graphical depiction of this. Suppose you're an agent. You have some outside option X. Alternatively, I offer you one draw from this urn. And I say, draw the item, okay? And then choose if you want the item or if you want your outside option. That's it. So I'm showing you a slightly different game. And if that distribution in the bag is G, then this C of G is going to give us how valuable is that over the outside option X. Now, obviously, if your outside option is very high, you're very unlikely to take the draw because you have to beat the outside option in order to take the draw. And if your outside option is low, you're going to take basically anything. Okay. But here is a, I think, pretty straightforward formula for the added value of search. This function is convex. It's going to turn out to be right differentiable. Very good. And so now we get to our first picture. So on the horizontal axis, we have the outside option X. And on the vertical axis, we have the additional value from search. And I'm plotting the C function for different distributions. So let me start with the red one. So this is if I have no information. I do know that the posterior mean is mu naught, is m naught, excuse me. If my outside option is the lowest quality item, it's equal to theta lower bar, then I'm going to accept, right? I have a draw. I don't know how good this is. The expectation is m naught, but I'm going to accept. And so if we look at the top left corner, okay, the value of search is just the expected value minus my outside option of theta. Now, as my outside option increases, My additional value from search strictly false because, well, sure, I'm going to accept this good as long as my outside option is less than m naught, but the value I get is potentially going to be small or maybe even negative. So my expected value is falling until we hit m naught. Once my outside option exceeds m naught, I'm just not going to accept a random draw because the random draw gives me m. All right. The other extreme is the blue. This is how I search if I have full information. I search from this bag, I see the exact quality, I choose whether to take it or not. And so we have not quite a triangle, but the area between the red and the blue, we can, excuse me, for any signal, come up with a G that lives in this space. So we just have to have it be decreasing and convex. So this is the space of signals that we have to play with, the area between red and blue. Any questions about that? Okay. So now I'm going to do another kind of intermediate game. Okay. Fix a G, a distribution G, and suppose the agent faces a contract that's offering G for free in every period. Suppose we know that's the case going forward. Then, okay, there's going to be some continuation value. So what's the value you get conditional on making it to the next stage? Call that U of G. Okay. When will I stop? I'll stop anytime the draw I get today is better than the discounted continuation. So that gives me a reservation value R of G. Okay, so throughout, U will be the continuation value, R will be the reservation value, which is just delta times U. Okay, I can't claim that any of this is novel, but this is basically what McCall did. Okay, there's going to be, according to this distribution, there's some reservation value. You're going to stop anytime you draw a good that exceeds in expectation the reservation value, and you're going to pass and continue searching anytime you don't exceed the reservation. But I can just rewrite this using the CG notation. Okay. And okay, why did I do this? Why am I showing you algebra? The reason is that this is a nice fixed point problem, right? We have an R and an R left and right side. And if we go back to our picture, so this is the picture we had. Let me draw the 1 minus delta over delta ray. What is this saying? This is saying whenever our C of G function, for whichever G we have, intersects this 1 minus delta over delta ray out of the origin, that's going to be the reservation. If you search for no information, if you search with no information, you have reservation value R lower bar. If you have full information, you have R upper bar. Anything in between is going to give you something in between. So the space of reservation values that can be induced are between this R lower bar and R. Here is just basically in words what I said verbally, in writing what I said verbally. Autarky reservation value, what you would search without information is R lower bar. The payoff is U lower bar. McCall reservation value, what you would search for in McCall's model if you had full information is R upper bar. The payoff is U upper bar. And so the maximum surplus that's on the table to be generated is U upper bar minus U lower bar. Certainly, it can't be the case that the principal is providing more information than providing full information. Okay. All right, now it's going to be without loss of generality to restrict our attention to pure strategies because our space is nice and convex. And it's also without loss of generality to restrict attention to equilibria in which the the agent accepts the proposed contract, because otherwise we could just sell no information for free, right? So it's without loss of generality to make that assumption. And so what's the stationary equilibrium? Stationary equilibrium says the same contract has to be offered today and tomorrow and the next day. Now, that's not a restriction on the strategy, on the actions available. It's a restriction on the type of strategy profile we're looking for. Okay, so there will be a stringle contract PG. The agent is going to have some continuation value, somewhere more than the autarky continuation value and something less than the McCall continuation value. We'll call that big U. And the principal will have a continuation value big V, which is going to be in between 0 and U upper bar minus U lower. And this contract has to satisfy the following conditions. First, we have that the agent is going to stop his search if his continuation value, discounted continuation value, is exceeded. Second, the agent's going to have a participation constraint. The price can't be higher than the added benefit of searching with the contract you buy versus searching with no information. Third is that the contract has to be optimal. The principal is making a take it or leave it offer here. So it has to maximize the principal's payoff, which is both the price they extract today, plus the probability of continuing to the next step, which is that the good does not exceed the reservation value, times the continuation. And then we also need that these continuation values are self-generating. Your expected payoff, which is what you have to kind of pay today or get paid today, plus the continuation value has to equal the U or the V, respectively. Okay. And I'm going to state the result in a second, but first let me show you. Let me just describe one signal distribution for you, which is going to be useful both in stating the result, but also it's going to show up in the proof. We're going to look for a particular form of pass-fail signal. Pass-fail signal says if it's below some threshold, fail the item, it's bad. Above the threshold, pass it. Okay. And that threshold is going to be exactly R upper bar for the purpose. It doesn't have to be, but for what I'm going to show you, R upper bar is going to be the useful pass-fail threshold. Remember, this is the reservation value for the agent who searches as if he had full information. Let G star be the induced distribution, and here's what C of G star looks like in the green. Okay. These pass-fail signals will have two kink points, and each kink point corresponds to the expected value conditional on either a fail or a pass, respectively. So if you fail here, it's saying the expected quality is whatever, just below 0. And if you pass it, it's you know, the kink point over there. One other thing that is not earth-shattering, and you could see it if you stared at the algebra for more than 30 seconds. The point of tangency with the blue line is going to be exactly at the pass-fail threshold. If you pass everything above R upper bar, you're going to be tangent to the blue line at exactly R. Okay. Here's a statement of the theorem. Not included in the statement, stationary equilibrium exists. Okay, but it does. A contract PG along with a pair of continuation values UV constitute a stationary equilibrium if and only if they satisfy the following conditions. Number one, the continuation value for the agent is U lower bar, which means that she searches as if she has, or her payoff is the same as if she was searching with no information. V, the continuation value for the information broker is U upper bar minus U lower bar, which means the full surplus is generated. But because the agent gets nothing, what are we saying? The full surplus is generated and extracted by the principal. Number three, the price is given here, which we'll notice is less than U upper bar minus U lower bar. What does this mean? This means that while the full surplus is extracted, it's extracted in dribs and drabs. You're not charging, you know, a one-time fee that gets everything. The fee is extracted over time. And the following 2 points say that together that the socially efficient search is generated. Okay, the agent is going to search as if he had full information for free. Now, I want to just kind of touch on this with respect to the first point. The first point says the agent's payoff is as if she had no information, but she searches as if she had full information for free. So this is where the word persuaded comes in. The principal is persuading the agent to search longer than she would kind of like to otherwise. Yes.
So it's not only socially efficient search, but also it reaches a socially efficient outcome, right?
Yes. So if we were to pre-line up the order of the balls in the urn or whatever, and you were to give McCall's agent the same sequence as the agent in this equilibrium, they'd stop at exactly the exact same point. Thank you for asking that, because I tried to put this in the paper and Teddy rejected. So what can you do? All right. Okay, so I'll sketch the argument that any stationary equilibrium has to satisfy these conditions. I'll give you one direction. The proof is going to be constructive, so we'll actually show you an equilibrium, which answers the question of existence, which I forgot to put on the previous slide. Okay, and it's going to be through a series of steps. I realized that, so how much time do I have?
You can have 10 more minutes.
10 more minutes, okay. Is the food good? Yeah, I'll try to be, if it's good, I'll try to be even quicker than this. All right. Okay, so suppose PGUV constitute a stationary equilibrium. Sorry?
Buy a signal about the food.
Yes, we should buy a signal about the food. Someone go eat it, come back, and then okay, so then PG has to solve a constrained maximization problem and fixed point problems from the self-generation. What's the maximization problem? We have to maximize the principal's profit subject to the agent's participation constraint. Now, the first thing to see here is that, well, P is only showing up in the maximization problem in the constraint, and the function that we're trying to maximize is also increasing in P. So this is easiest. Okay, this participation constraint is going to bind in any equilibrium. If not, the principal could just raise the price by 1 cent, right? That's not going to throw off the future incentives. We're just dealing with a change today, but it will put more money into the profit of into the pocket of the participant. Okay. So this has to bind, which means let me just rewrite P with the C G hat delta U minus C G naught delta U. Very good. And then if we just take the previous equation for the fixed point and plug it in down here, what we see is that this is just exactly equal to U lower bar. Okay, this is not a deep point. It's really just saying there are two things going on. The principal is making a take it or leave it offer. We're also dealing with a stationary equilibrium. So the agent can't threaten in the future with, kind of, if you do something bad, I'm gonna punish you in the future. And so the agent has no bargaining power. The agent's going to be squeezed as much as possible. Okay. Very good. Okay. And so what does that tell us graphically? If our black curve just so happens to be the equilibrium, it's not going to be, but if it happens to be the equilibrium G, or represent the equilibrium G, then the price is going to be given by the vertical distance between the red line and the black line. I mean, that's just what this is at our lower bar. So now we know what the price is in any equilibrium. Okay. The second thing that I want to say, it's not just the height in some sense of the CG line that's going to be relevant. It's also going to be the slope at our lower bar, excuse me. And so recall that this is the definition for C. We can take an integral. This is going to be right differentiable, and the derivative is going to be g of x minus 1 at point x. And so what does this tell us? This is the where we left our problem. Well, let's just go ahead and plug in for a g of r lower bar right over there with this right derivative plus. Okay. And so what do we see? We see that the object that the principal is trying to maximize is really the height of the function, but also they care about the slope. So we're trading things off here. So we have some trade-off between height and slope. All right. Next thing I want to try to convince you of, and this will basically be no proof at all, but it suffices to consider a pass-fail signal. There's a binary action that's being decided upon. A pass-fail signal will suffice. The way to see this kind of mechanically is you give me this, or graphically, you give me this black G function. Here is a pass-fail signal. Why is it pass-fail? It has these two king points. Okay. It has the same price because it has the same height at r lower bar. And I've drawn a tangent to the black curve, which means that it has the same slope at r lower bar as well, which means the value here of the objective function is going to be exactly the same for the black and the green. Okay. So for the rest of the proof, I'm just going to consider these pass-fail signals. But actually, it suffices to consider, or rather, we have to consider tangent pass-fail signals. Why is that? Tangent to the blue is what I mean. Well, if we're not tangent, we could just shift it up. What's happening here? We're not changing the slope by shifting it up, okay, which means that the continuation probability is exactly the same. But by shifting it up, I am charging more money from the agent. So what is it saying? If your pass-fail signal is not tangent, which means you're actually having some randomization going on, this is going to end up being profit-inducing, profit-improving. Excuse me. Okay. So we've now taken this kind of ugly problem and transformed it into, we're searching for a single, a maximizer of a single dimension, which is just the points of tangency. The lowest point that we're going to consider is this r lower bar. The point of tangency is not going to be lower than this. If you actually tried to do it, you'd increase the slope or make the slope more negative, and you'd actually reduce the price. So that's no good. There's also a maximum pass-fail signal that pass-fail threshold that we can consider. That's at this point here. And what's this saying? This is saying conditional on the good failing, the expected value is r lower bar exactly. If you tried to pass more objects, if you tried to pass fewer objects, you're pulling in even more good quality items. At that point, it's not going to be worth it for the agent to stop if you're telling him, hey, you should stop because that item's too good. So it's saying you can't just say, who's the smartest person we know? Terrence Tao, maybe. Okay. We can't just say that like Terrence Tao is smart, everyone else is dumb. Don't hire them because, okay, that's not really, there are Harrys out there. Sorry, Harry, you're the second smartest person. Good. Okay. So a little bit more algebra. We have to pick a point of tangency x. All right. We know that at this point of tangency, we're going to have a flat region between r lower bar and x based on this pass-fail signal structure, which means that we can read off the slope, of course that doesn't work, as exactly f of x minus 1, the point of tangency, not this r lower bar. And the price we can do some algebra to get in this form. And so I'm going to put this all together. Here's where we left off. Right, we want to solve this maximization problem. I'm going to replace, this is, remember, the price, and this is the slope, with the two objects I just put on the previous slide. We also have the self-generation condition, right? We have the v on both sides. And so let me just solve that out. Here is the problem that we're now solving. Okay. the principal is picking a point of tangency to maximize the value of search for that point of tangency. I've just called this U of X minus U lower bar, which is the value of search from author. What is this? This is just saying we want to maximize the total surplus now. There's no notion of extracting things. We've turned our problem into a profit maximization. Excuse me, into a surplus maximization. And well, we already know what the optimal point of tangency is. We know how to maximize the surplus. We calculated that that was U upper bar minus U lower bar. The point of tangency corresponding to generating the payoff of U upper bar is R upper bar. And that gives us exactly this pass-fail signal distribution that I told you before I stated the result. What is this doing? This is failing all items below the McCall reservation value and passing all other ones. The agent is incentivized to follow the search recommendation, right? So if there's a fail, the item's quality, expected quality is somewhere down here, which is less than our lower bar. You should stop. If it's above this, then it's above our lower bar. This one's kind of even easier to see. Okay, so you will stop if you're told to stop. Now, there were two other conditions about the theorem, and then let me, I guess I have to wrap up, which have to do with socially efficient search. So let me very quickly say what these buy us. Any equilibrium signal has to be flat and has to exactly hug this green line between our lower bar and our upper bar. What is that saying? That's saying the principal has to pool marginal quality items with sufficiently low quality items and fail all of them. Why is that? Because if the principal said, okay, this guy is just 1% less than your stopping threshold, the agent would say, great, you're charging me money tomorrow. I want to stop early. I don't want to pay you. My continuation value is lower. They would stop. So it's precisely by pooling that the principal is able to say to the agent, hey, I know you want to stop for marginal quality goods. I'm not telling you which ones those are. So it's precisely this region that has to hug this line. Otherwise, we can do kind of crazy things, right? So, for example, we could have this optimal lower censorship test, which says, I'm going to fill all items below our lower bar. And if it's above our upper bar, I'm just going to tell you the exact quality. And then I'll have the exact same search behavior. And so here is the corollary of that. If G is supported by a stationary equilibrium, then it's constant over our lower bar to R. So we have this pooling over this region. And again, we had this, we could sell the testing technology if we didn't have commitment. And so what does this tell us? The value of commitment is not high, at least in this simple model. There's no actually intrinsic value for the principal of being able to commit. And we focused on stationary equilibria. It turns out the principal doesn't really need to consider other ones either. They're very happy to maximize it. So let me just say that we've considered some extensions. I'm over time. I won't talk about them. We are looking at a new paper that studies non-stationarity and competition. I'm very excited about this result, so let me tell you this. It turns out competition, introducing more principles to compete with one another, is one, good for the agent, and two, bad for efficiency. So it actually turns out that if you care about efficiency in this market, a monopolist is the right way to go about it. Competition's bad. All right. So let me end there. Thank you very much. Sorry to keep you from lunch. I'll be around for any questions.